This lesson's about power in electric circuits. First, remember that electrical devices, which we could also call loads, transform electrical energy into other forms of energy. And also remember that power is defined as the rate at which energy is transformed or transferred. Power is equal to delta E over delta T. So let's say that we had a simple circuit like this with a cell and a bulb, and we wanted to figure out the rate at which energy is being transformed at the bulb from electric energy into light and heat energy. We'd be asking to work out the power. So power is equal to the change in energy divided by the change in time. But remember that the change in electrical potential energy is equal to the charge that is moved multiplied by the potential difference through which it's moved. In other words, it's equal to delta Q times V. And remember, I could be using V or delta V here to mean the potential difference. They get used interchangeably. I'm going to use just V for simplicity. So that's my numerator. This is the expression for the change in electric potential energy, or the work done on a charge. It's equal to the charge multiplied by the potential difference through which it's moved. And our denominator is still delta T. But recognize now that this is our definition for current. Current is the rate at which charge is moving. So simplifying this, I get current times potential difference. In other words, if I wanted to work out the power at this bulb, I would put an ammeter in series with it to measure the current through the bulb, and I would put a voltmeter in parallel with it to measure the potential difference across the bulb, and then I would just multiply those two things together. Power is equal to current through times potential difference across. That's one expression for power. Using our definition of resistance, resistance is equal to voltage across divided by current through, we can work out two more. Rearranging this expression, I get V is equal to IR. So now I can put that in here. V is equal to IR. So power, which was equal to I times V, is equal to I times IR. And so power is equal to I squared R, the current squared times the resistance. That's one new version. Another is to rearrange here and see that I is equal to V over R. So I can go back up here and plug V over R in for that I and leave this V in place. So power is equal to IV is equal to V over R times V, which is equal to V squared over R. So now I have three different expressions for the power being transformed at a component in a circuit. I have power is equal to the current times the potential difference. I have power is equal to the current squared times the resistance, and I have power is equal to the potential difference across the component squared divided by the resistance. And all of those will be useful depending on which information we're given in a problem. So that's power in electric circuits.